Hey, hello everyone. Hello everyone. Today I want to talk about reactive programming because apparently that's what I'm specialized in. But I want to talk about reactive programming from a slightly different perspective, from a grumpy old man perspective. But before we start, the main goal of this presentation is that you have to be this tall in order to do reactive programming. And by saying this tall, I mean you have to have a certain level of expertise to actually gain something from reactive programming, because otherwise you're just going to shoot yourself in the foot and you're going to lose both of your feet. So, do you know who said it, by the way? Do you know from which movie is it? Yeah, it's from movie Taken. But just as about his daughter, he could have said it about reactive programming. It was Liam Neeson in the movie Taken. My point is, if you're really skilled, even if you're really skilled in reactive programming, whichever flavor you choose, you can harm yourself and you can harm all the people in your team, in your company, and basically whoever's going to support your code base. Okay, so let's start. Who am I? Not because I want to introduce myself, but maybe you want to know why am I actually so grumpy and do I have any experience with that. So I built quite a few complex reactive systems. And I'm not really proud about the complex part. It just so happened that they became complex because they're distributed and they're reactive, and that's how the world goes. Moreover, I was supporting and I was maintaining an Akka cluster of more than 1,000 remote nodes. So really big one in a big financial institution. It was doing some really complex distributed math calculations. They were selling maths, they were selling bonds, CDSs, contract default swaps, and so on and so forth. Pretty serious stuff in Akka quite a few years ago. By the way, this system was written in 4 different languages at the same time. And I know it because on a single stack trace, there were 4 different languages. It was Java, Scala, Clojure, and a homegrown language that they invented in a company. Pretty horrible. I also managed to support more than several thousand requests per second on a single machine, which is totally possible if you're doing reactive programming, and only if you're doing reactive programming, so you have to remember about it. I also managed to beat C10K problem. If you don't know what C10K is, it basically means managing more than 10,000 concurrent connections on a single machine. And if you think about it, with a typical thread per connection model, this means more than 10,000 threads on a single JVM, which is pretty much impossible, or at least not something you want to do on production. With reactive programming, whichever flavor and whichever framework you choose, this is totally doable. C10K or even C100K. I even saw articles where people were handling 20 million concurrent connections on a single JVM using reactive programming. This is really serious stuff. So honestly, I love reactive programming, and I think it's a really, really powerful tool. But this is not what this presentation is going to be about. You know what? I even wrote a book about reactive programming, a book that has reactive in the title, but still, today I want to tell you that reactive programming is probably not a good solution to your particular problem. So I'm going to be a bit grumpy, and I'm really sorry that I'm closing a conference with something that's kind of sad, and I will be arguing that that's not the perfect tool all the time, but still, I think you have to know my experiences. All right, so let's start. Do you know this Chinese saying, may you live in interesting times? The funny part about this saying is that it's actually a curse, because no one wants to live in interesting times. Interesting times means war, famine, revolution. People want to live in boring times. People want to live in times when everything is stable, everything just works, and they don't have to particularly care what's going to happen tomorrow. So I coined another saying, may you support interesting code base. And you know what I mean by saying interesting? Remember the last time you're doing a code review, you're looking at a patch and you're looking at someone's code and saying, oh, that's interesting. That's a very bad sign. When you're looking at someone else's code and it was just written so you're fresh, and maybe it's your own code and you're describing it to someone, and when you're looking at it and you're thinking, wow, that's interesting. I used the strategy pattern using monad in so interesting way. That's definitely not what you're aiming for. Your code should not be interesting. And this is a curse as well, and I'm going to show you this in quite a few examples. So imagine you're building such a system. This is like a very, very simple requirement. It's not a hello world, but still it's something that theoretically you could find in your normal system. So what is it? Fetch user by username, do this and do that, quite a few steps. So imagine you're writing it in any language. Let it be, well, after previous presentation, you know like 100 different languages. So imagine it's Java, Scala, Kotlin, Groovy, whatever. And every single language is going to be fairly straightforward. You don't really have to be a programmer to understand what's going on here. Fetch user from database, if there's from something, from web service, if user is not in the database, store it, so on and so forth. Probably the most sophisticated part of this code is the Stream API, which is like 5 years old, 4 years, something like that. But honestly, this is the only reasonable way to write this code in 2018. Apart from the Stream API, you could use a for loop. And that's why it's so straightforward. There's literally no other way to make it simpler or no other way to make it more reasonable. And if you put a junior programmer, and there's absolutely nothing wrong with junior programmers, if you put a junior programmer or if you put a quality assurance engineer in front of this code, and he looks at it, he knows exactly what's going on here. If you need to add a small change, like if your total cart is greater than $100 or something, add a discount or whatever, you know precisely where to put this code. It's dead simple. But one day, you came back from a conference, and my talk wasn't the last one. You came back from the conference, and you heard about this brand new, shiny reactive programming, so you thought, it's great. I want to rewrite everything. Because that's often what happens after a conference, and I've been there. So here it is, the first line, fetching a user from a web service or whatever. No matter which framework you use, is it Reactor, RxJava, is it Completable Futures, is it Akka Actors, it's going to be looking more or less like this. So you're fetching a user from something, and then rather than having a user in return, you get some sort of a box, like a future, a mono, an observable single, it can be a future from Akka framework, whatever. It's going to be a container that somehow signifies that this is an asynchronous source of data. Knowing that it's a mono or single or completable future or whatever, you know that this is going to arrive a little bit later. So here you are. That was fairly simple. Let's proceed because it seems like we're going really well. Now another method, database contains. Obviously, it cannot just return Boolean because everything is asynchronous. That's the point of reactive programming. Everything is event-driven. We are supposed to fetch data from multiple sources, react on events, and so on and so forth. So suddenly, we get a future of Boolean. A future of Boolean basically means you're going to get this Boolean, you're going to get true or false sometime in the future. Plus possible failures and so on and so forth. But in general, that's how it works. So not a big mind shift so far. Okay, but how do you change this if statement? How do you rewrite this if statement? And it actually becomes a little bit painful, and there's definitely more than one way to do it. You could use a flat map, you could use other operators, but something along these lines. I actually put some comments on the right because I wasn't sure which types are flying here. And if you look really carefully, you're going to get something like a mono of Boolean, then you're going to have an empty mono, then you have an operator that switches from one stream to another. And by the way, the same applies to every single reactive framework. The syntax slightly changes, but that's pretty much it. All right, so this was the original code. I'm going to spare you the rest of the transformation. I'm just going to show you the final steps. So take a deep breath. I actually spent quite some time rewriting this, and even making it compile was not that straightforward. And I came up with this. This is like, it's basically flat map. It's a program about flat maps. And it works. It seems to be working. It has one great advantage over the previous implementation, which is totally not visible. Sending emails is concurrent in this version. Anyone spot it? Because you have flat maps somewhere and it's asynchronous, which we know because it's implicit. This is terrible. This is how a typical reactive program works, irrespective to a framework. All right, so what can we actually do about it? We started with something really simple. And this is the code I really want to support because it's damn simple. And it turned out to be something like this. How did we get there, you might ask? Okay, have you ever heard the term ubiquitous language? It's this term coined by domain-driven design enthusiasts, and it's the idea that your software should be expressing your domain. So if you're doing a software about insurance, for example, then in your software you should see everything about insurances, like a policy, an emergency, an accident, and so on and so forth. If you're doing something in, I don't know, pharmaceuticals, then your code should be about medicine, pharmacy, so on and so forth. If you're writing a software about blockchain, then God, please stop. But nevertheless, the idea of ubiquitous language is that when you're reading your code, it should be screaming about your domain. You should have as little distractions as possible. So I read this article about the other day. It was about very functional programming. It was actually about category theory. And the guy was asking, is your domain about semigroup, monoid, monad? I don't even understand half of these terms. And I kind of honestly don't even want to know. So he was asking, is your core domain mathematics? If not, why is your code cluttered with things such as Kleisli, comonoid, and so on and so forth? It makes no sense, because you are not writing a software for mathematicians. You're writing a software for insurances, for pharmacies, and so on and so forth. And one great quote, you want to have everyone on your side. So software developers, QAs, and the business people. So the guys who actually give you the requirements. You want to speak the same language as them. And if your program is all about reactive something, then good luck finding them, because no one is going to understand what you wrote. So another question is, and once again I'm paraphrasing what was there, is mono and flux pervasive in your domain model? Are you programming against monos and fluxes? And my point is, most likely you're not writing software about infectious diseases. Mononucleosis and dysentery, these are infectious diseases. Your software is not about sicknesses. Your software is about insurance, pharmacies, blockchain, whatever, but not about mono and flux. Someone was showing this tag of keywords or tag of words that are most common in the source code during this conference. And it turned out that most of us are writing software about strings. That string is the most common word in the code base. And I don't want my code base to be about strings. My code base is about cars, loans, medicines, whatever your domain is. It's not about fluxes and monos. It's not about flat maps. These are just implementation details. They should be completely transparent for all of you. All right, so let me ask this question. What's the universal measure of code quality? I'm pretty sure you are doing code reviews quite often. What does it mean that the code is beautiful, that it's great? Can you give me one word, one adjective? Yeah, WTF. Many people are actually replying WTF. WTF basically means how many times when looking at the code I was saying WTF. You saw this comic many, many times. Something more? Come again? Readable, yes. So readable, one more thing. So looking at the code, I'm going to actually get back to it. I have a few hints for you. Simple. Can you agree that the code is simple? It's a good quality of, a good measure of the code quality? I can actually barely see you, but I see a few people nodding their heads. Nevertheless, there are people who think that monad transformers are reducing boilerplate. This is an actual quote from some blog. I don't understand this sentence. Maybe the guy is right. Maybe it does reduce a boilerplate. But my point is, simplicity is a matter of taste, actually. And it also depends on your experience. So a few other hints. Test it. A good code is tested. Well, maybe, but if you have a really poor code and like poor developers or too experienced developers, just the fact that your code is tested doesn't mean that the code is good. You might have a crappy code and a crappy tests along with the production code. And it's better just not to have any of them in the first place. So one more thing, open, close, solid, high cohesion, low coupling, cyclomatic, dry, all of these will really help you during recruiting, but they are very, very abstract terms. What you really want from a code base, and just to recap, the question was, what is the universal measure of code quality? And you know what? I believe it's boring. When code is boring, it means that I am not distracted with the details. I am not looking at frameworks, I'm not looking at libraries, tools, whatever. I'm just looking at the pure business logic. When I'm looking at a pull request, and I'm doing it quite often, I'm not getting distracted by the details of futures and schedulers and the way things are composing with each other and maybe the operators that are being overloaded here and there. No, when I'm doing a code review, what I'm really counting on is that someone's going to tell me, you know what, you didn't cover this business use case here. I believe this code is not going to work properly because you forgot about applying a discount or checking this other account or whatever. And that's the perfect review because it focuses on the essence. And that's what I'm aiming for. So I don't really care about frameworks. So many people were talking about Spring and how to avoid it. The same applies to reactive programming. So keep that in mind. All right, ever heard the term 10 times developer? The 10 times developer basically means this mythical guy who is like 10 times faster than everyone else in the team. And it seems like everyone is just miserable because he's so fast and so productive. And it might be the case with reactive programming if you're so great, you read so many books, so many blogs, you have such a great experience. But I believe that being a 10 times developer is just helping 10 other developers to become more productive because you're just one person. If you can make the whole team more productive, if you can help all the others to be productive from day one, rather than making it harder for them because you're writing such a complex code, that's the great benefit. And if you're a 10 times developer just because you're using so fancy tools that no one else understands, you're not a 10 times developer, you're an asshole developer. All right. You don't want to have it. Okay. You have to ask yourself a question, what are you really optimizing? Because in the end of the day, you actually want to push some software to production and it's supposed to make some money. There are 3 factors of software cost. It's the cost of the actual development, so the cost of developers who are sitting there tapping their keyboards and writing code. There's the cost of hardware, so you actually have to deploy the software somewhere, unless it's serverless. Okay, I'm going to just skip this joke. And then there's maintenance. So you have to spend weeks, months, years supporting your code base, making bug fixes, adding small features, and so on and so forth. And these are 3 things that you actually have to take into account when developing new software. So how does it look? I wasn't actually doing any research, it's just my gut feeling, but I saw people who were doing it. I was trying to figure out what's the total cost of building software compared between blocking and non-blocking or reactive approach. This is blocking code, and on the x-axis you see the scale of the company, so how many customers, the data volume, whatever. And on the y-axis it's the cost of the software measured in cloud coins, because it's not based on any real research. So it seems like when you're doing blocking programming, the thing that you already saw, this very tiny code snippet that didn't have any futures, monos, and so on and so forth, starting is really, really simple. You just write a bit of code. Everyone can write code like that. You just deploy it to any machine anywhere, and the cost of maintenance is also really minimal. Why? Because the code is so simple. So it's very easy to make changes, it's very easy to rewrite, it's very easy to test. Of course, once the scale of the company grows, which means you have to handle more data, you have to handle more requests from the customers, you suddenly realize that you need more and more hardware because your hardware doesn't scale that well. The cost of maintenance is also skyrocketing because it turns out your one single database and one single node that you're just scaling out doesn't work that well. And it turns out this way of writing software isn't particularly scalable. And that's what reactive programming is supposed to solve. So let's see how it looks. In terms of reactive programming, the development is much, much more costly. Why is that? Because you need more experienced developers. or you have to spend quite a lot of time up front just figuring out how to use a particular framework. We all know Java, this is a prerequisite, but you still have to know all these frameworks. How are they interacting? What's the threading model? Where can you block? And so on and so forth. So this is pretty terrible. And the problem is that you have to know all of this from day one. Otherwise, you're going to be really miserable on production trying to maintain it. The cost of hardware is minimal because reactive code, the non-blocking code, scales insanely good. You don't need that much memory, you don't need that much CPU. And that was the idea of reactive programming. So that's fantastic. But also the costs of maintenance are much higher. So how do these two approaches compare? What is the bottom line? Where can you see the difference between the first one and the second one? So here it is, with no particular scale here. It seems like at the very beginning writing blocking code is much cheaper, and this shouldn't come as a surprise. Everyone can write blocking code. This is what we are taught in the first chapter of every Java book or virtually any other language. However, there is some point at which reactive programming starts to pay off. There is some point where the costs of hardware, pretty much hardware alone, outgrows the costs of development, the cost of maintaining. And I call this point the Netflix point. Netflix being the parent, the grandparent of everything microservice and everything distributed. They are accountable for like 10–20% of the whole internet traffic these days. They are definitely at the right-hand side of this line. They have to use reactive programming because they are already paying hundreds of thousands of dollars for EC2 instances on Amazon. People on the left-hand side, on the other hand, are perfectly fine with blocking code. They don't need blocking code because simply they don't have such scale, and investing in reactive programming doesn't really pay off. So you have to ask yourself a question. Are you Netflix? And I'm going to give you a hint. No. And it's not like, well, for the most part of my career, I was in Netflix as well, meaning I wasn't dealing with such a scale as Netflix. It's just my recent company where reactive programming actually makes some sense. Despite the fact I was doing reactive programming much, much earlier, which means I was over-investing and it didn't make any sense. It might for you, you might be Netflix, and by Netflix I mean Netflix scale, or maybe someone's from Netflix. But you just have to make a conscious decision. All right, do you know Little's law? It's perfectly beautiful, very, very simple. It basically means how many threads, how many CPUs, how many workers, how many counters in a grocery store you need to handle given load. So L is the number of workers, lambda is the throughput, so how many new requests you have per second, and W is the average time it takes to handle one request. It sounds a little bit abstract, but so I'm going to give you a very short and sweet example. Imagine Tomcat. A typical Tomcat in a blocking configuration has 100 threads. I'm pretty sure you all know how Tomcat works. It basically needs one thread per single client, per single connection. So having Tomcat with 100 threads, with 100 milliseconds per each request, 100 millisecond average for a request is not that much, actually. You can compare it with your own systems, but 100 milliseconds is not something that totally doesn't make any sense. So 100 milliseconds per request, that's enough to parse JSON, put it in a database, and send JSON back, which is 99% of the systems we're doing. So in this configuration, according to Little's law, you can handle 1,000 requests per second. 1,000 requests per second on a laptop with no reactive code, just like that, according to Little's law. That sounds a little bit surprising. All right, ever heard of space-time trade-off? A space-time trade-off is this idea that sometimes in the computer system, you are trading space, as in memory, for time, as in CPU or waiting time. The simplest example of a space-time trade-off is caching. When you are caching some data because you don't want to compute it once again or you don't want to fetch it from somewhere, you're just putting it into memory or on disk. You are trading off space for time. So how does it work? Imagine you have the exact same trade-off, but between humans, software developers, QAs, and so on, and hardware. What if I told you that in some cases, software developers are more precious because they're quite expensive, that you do want to spend as little time and as little expertise on software development as possible, meaning writing blocking code, the simplest possible flavor, a blocking code, and kind of accepting the fact that you're going to need more hardware later on. You're on the left-hand side of the Netflix point, remember? But maybe you are on the right-hand side of the Netflix line, and in this case, you do want to invest more in developing the software because you want to save some money on hardware. It's your choice, but it has to be a conscious choice, not something you're just heard about at the conference and you want to try out the new shiny tool. All right, so let's talk about maintenance, cost of maintenance. The maintenance is this point where you actually deploy something to production and then you have to support it, the often overlooked part of the software development. So stack traces are something that I miss so much with reactive programming, and we're going to get a little bit more practical at this time. So this is a stack trace I captured in IntelliJ one day. It has 200 lines. It's a monster. It contains like everything. There's like Spring intertwined with Hibernate, intertwined with aspects, intertwined with pretty much everything. Just to give you a rough comparison, this is the tallest building on Earth. It's 160 floors. It's much smaller than the stack trace. But you know what? I still love stack traces. I still love stack traces because they allow me to see exactly what's going on my machine. Just a very quick example. One day, a database pool was telling me that it's not capable of fetching a new connection from the data source. There's some internal pool and it tries to fetch new connection, but after 30 seconds it timed out saying there are no more connections. So what is my first thought? What do you think? There are no more connections in a connection pool in your database. What do you think is the problem? Yeah, there might be a resource leak, which is actually a good catch, or you have like too much traffic, your connections are occupied for too much time, you're making too complex queries, and so on and so forth. Just by looking at the stack traces, and I'm not going to be going too much into details, I figured that at some point this application was doing some transaction synchronization, something callback, and after making commit, it was also sending a message to ActiveMQ, which is a fairly decent thing to do, actually. Once the transaction is committed, I want to push something to a message broker. Actually, this was suggested during one of these talks, during this conference, and it's a good idea. But it turns out that in Spring, the connection is still getting hold while this callback is, okay, so many details at this point, but just by looking at the stack trace, I managed to figure out that it wasn't a database, it was ActiveMQ that was holding the resources. And what was the solution for this hiccup with the data source? Restarting ActiveMQ. Welcome to IT, like everything is interconnected. But what's the moral of this story? Just by looking at stack traces, I can figure out what the application is doing from top to bottom. It tells me the full story, the full picture. On contrary, with reactive programming, and if you have any experience with that, you know it all too well, stack traces are meaningless. Stack traces typically start with some thread pool, and you have no context. You have no idea where this particular process started. And this is, by the way, from a Netflix blog. It's difficult to follow requests. We have some tools like contexts in Reactor. We have trace IDs, which we can propagate, and so on and so forth. Nevertheless, tracing what's going on in a reactive application is much, much harder. So, once again, unhandled exceptions, these types of issues have proven to be quite difficult. And this is Netflix. They are on the right-hand side of the Netflix line, obviously, and still they find it really hard to troubleshoot these types of issues. All right, exceptions from hell. We already saw a few exceptions so far, and I was trying to convince you that exceptions aren't that bad, especially when your choice is having them and not having them at all. So let's look at this very tiny piece of code. It could be Reactor, it can be RxJava, it can be completable future, whatever. I'm just having a stream of data and I'm transforming it. It turned out that one of these transformations returns null, which is forbidden in most of these frameworks. And how do you tell that something returned null, or you're trying to dereference a null in normal Java program? How can you tell that there was a null in Java program? Null pointer exception. And null pointer exception tells you exactly what was the issue. In Reactor, it looks more like this. And if you look really closely, you will still not find the source of the problem. You have no idea which one of these three operators actually returned null. And this is like the simplest case ever. Many people ask me what's the difference between Reactor and RxJava. They are so similar that even the stack traces are similar. So this is RxJava, this is Reactor. Both of them are meaningless. Okay, timeout exception. One more thing that's really easy once you have blocking code and extremely difficult to debug when you have a reactive code. When you have a blocking code and you see timeout exception, you get a full story which line precisely was blocked and why timeout exception appeared at this particular place. For example, fetching a connection, waiting for data from web service, so on and so forth. If you get a timeout exception in reactive code, this time it's akka, I believe, yeah, somewhere along these lines, not a single line in this stack trace reveals where the timeout exception occurred. I have no idea. It just popped out somewhere in the logs asynchronously from a thread that I had no idea exists. And it's just there, and I literally have no idea where to start. It just appeared out of nowhere with no meaningful context. Okay, so let's go and let's wrap up with a few practices if you already went through this one. Went through reactive programming. So the best reactive system is the one that doesn't have any threads at all. And believe it or not, Reactor and RxJava by default don't use any threads. Everything is synchronous because that's the fastest way. So if you don't forcibly, if you don't explicitly set a scheduler or a thread pool or whatever it's called, you won't get any threads at all. And that's the most performant way because context switching actually costs. So before you start jumping between one thread and the other, think about the cost of switching between these. Reactor pattern, actor, SPSC. SPSC stands for single producer, single consumer. All these patterns are built around the idea of single thread, or at most two threads. That's the simplest case because it's actually the easiest to debug. All right, you have to remember about order. When you're doing normal blocking code, the order is pretty obvious. You're just reading from top to bottom. When you have a for loop or a stream in Java, you know that data is going to be processed from the first item to the last item. Some operators, and the same applies to akka, completable future, whatever, some operators will, by design, change the order of your operations. And you have to remember about it. Two of these operators, concat map eager, and I believe concat map, keep the order. The other two do not. Which means that this is actually by design. It means that you're processing data as it's completed. But it's also a source of some very subtle bugs. For example, once in a while, your requests are going to get mixed, and it's really hard to spot. One more thing, DDoS, distributed denial of service, was never that simple. For example, flatmap by default has a limit of 128 concurrent things, processes, or whatever. This means that if you don't pay enough attention, your single reactive component, which is blazingly fast, is going to bring down all the other components surrounding it because it's so fast that no other component can keep up with it. And you just have to be a gentle citizen. You cannot forget about the other components because you're going to bring down everything else. And let's talk about monitoring. I have a lot of experience with monitoring, especially in the microservice ecosystem. How do you monitor a system like that? Well, I really enjoy an architecture called SEDA, which is Staged Event-Driven Architecture. It's this concept where all the components, whatever whatever you consider a component, all the components are communicating with each other, not synchronously, but via queues. So you want to say something to another component, another process, another class, whatever. You're sending a message to this component asynchronously, and it has a great benefit. If you're monitoring such a system, you know precisely which queues are filling up and which ones are empty. If one of the queues is filling up, it means that either someone is producing too much or someone is not consuming fast enough. And by the way, queues are everywhere. Any of you ever used synchronized keyword? I'm pretty sure you did. Yeah, I see few people. The rest of us are like, I don't know, ashamed or sleeping already. So the synchronized keyword is basically a queue. It's a single thread that accesses a resource, and second, third, fourth, hundreds of other threads that are waiting for this resource, for a method that's surrounded with synchronized keyword. The only problem with this approach is that you have no control over this implicit queue. You have no idea how many threads are waiting for this block. So rather than having things implicit, let's just have an explicit queue. So I really enjoy this. I really enjoy this architecture. And the best part of it is that you have queues, so it's easy to monitor. Do you know any very popular production system, production framework that uses this approach of components communicating via queues and messages? Yes, it's Akka, definitely. So in Akka, and this is the most beautiful example of this architecture, you have actors that are communicating with each other. So if you want to know which actor cannot keep up with the load, you just look up what's the length of the queue in front of this actor. And the queue is known as mailbox. So mailbox is this place where pending messages are waiting for the actor to process it. The problem is that in Akka 2, so many, many years ago, the mailbox size, so this most essential metric, was removed. And I sort of understand their description. They said that measuring the length of this mailbox in a distributed environment is kind of hard, it's never reliable, it's never accurate, so on and so forth. So I kind of got along with it. I have Akka, but without the benefits of knowing the length of the mailbox. However, if you buy Lightband Telemetry Enterprise Suite, suddenly the metric appears again. However, you have to pay for it. The most essential metric in the whole distributed system. And if you're designing a system yourself, think about it. Think about making queues explicit rather than implicit. All right, what are the key takeaways? And I'm wrapping up right now. First of all, Spring Boot will change everything. We didn't talk much about higher level frameworks, but starting with Spring Boot, what used to be such a simple endpoint, just finding a user and repository, returning 200, 400, depending on what we want. Then a slight flavor of functional programming came in, so now we're using optionals, and it looks more or less familiar to us. And now we have Spring Boot 2 with webflogs and all the other goodies. And you have to be prepared for it. Even if you don't like this code base, you will sooner or later find it in your repository because people around you will start using it. And you just have to make sure it makes sense. It has some great benefits, and it actually seems fairly simple just looking at this, but still, it's a lot of burden to your cognitive abilities. Reactive programming is really awesome. I was mentioning it to you in the very beginning, what kind of things you can do. Remember C10K, C100K problems? Handling thousands or hundreds of thousands of requests per second on a single machine? That's perfectly doable. So I truly believe reactive programming is a great tool. You just have to make, especially in the era of microservices, where one request is spread across tens, maybe 20, 30, 40 different services. And concurrency, making these parallel, is essential for making your system actually fast. So you have to know a little bit of reactive programming just to have tools for concurrency, basically. Nevertheless, you have to ask yourself a question, are you really benefiting? Are you doing reactive programming because you have to? Or you just learn about new shiny tool and you think that it's going to be better, even though it doesn't really bring you any benefit. I want you to make a conscious decision in your next project, because it might be the best or it might be the worst technology decision ever. And thank you very much.